Thanks for.
So it's my pleasure to introduce Jiahao Qiu from Beijing University, who will talk about top-nilpotent developing semigroups and pro-nilsystems. Okay, go ahead.
Thanks for Jonathan's invitation. I'm glad to give a talk here. And in this talk, I mainly discuss the relation between the pro-nilsystems and their enveloping semigroups. The notion of enveloping semigroup introduced by Alice in 1960 was proved to be a fundamental tool in the abstract theory of topological dynamics. And dynamical properties of a given system can now be viewed through the algebraic. Oh, okay. We use X row to denote a compact metric space, and HX the group of self homomorphism of the X of the space, which is endowed with the topology of uniform convergence. With this topology, HX is a Polish topological group for a homomorphism T of the space. We call the pair XT is a topological dynamical system, or just a system. So a system is called a minimal if every point have a dense orbit. Let's recall some classical result. In some sense, an equal continuous system is the simplest system in topological dynamics. Here is a definition. So in the study of topological dynamics, one of the first problems is to characterize the equal continuous structure relation of a given system. That is to find the smallest closed invariant equivalence relation such that the factor induced by this is an equal continuous system. It was shown by Alice and Gottschalk that the smallest equivalent relation containing the regional proximal relation is the equal continuous structure relation. Similarly, similarly, we can consider the distal structure relation of a given system. It was shown that the smallest equivalence relation containing the proximal relation is the distal structure relation. In order to study the asymptotic behaviors of a system, Alice introduced a very powerful tool called the enveloping semigroup of a given system. It is defined as the closure of the set of the all action in the set of the maps from X to X with its compact, usually non-metrizable point-wise convergence topological. Actually, enveloping semigroup of a system is metrizable if and only if the system is equal continuous. Alice proved the following beautiful theorem. He proved that actually a system is distal if and only if the enveloping semigroup is a group, and a system is equal continuous if and only if the enveloping semigroup is an abelian group, if and only if the enveloping semigroup is a group of a homomorphism. So based on Alice's result, it's natural to ask can we give a fine classification of distal systems using enveloping semigroups? But as we said at the beginning, explicit computations of enveloping semigroups are very hard. It was Glassiner who gave the first non-trivial result in 1993. It proved that if a minimal system has a good property, then we can build a bridge between the enveloping semigroup and the dynamical property. Precisely, if the regional proximal relation is generated by a torus, then the following are equivalent. The first one is the enveloping semigroup is a two-step nilpotent group. And the second one is there exists a two-step nilpotent Polish group of continuous transformations of X and acting transitively on X. And also there exists a closed co-compact subgroup such that the action T is T belongs to G and K is in the center of the group G. The commutator subgroup of G is included in the torus. And the most important is that the homogeneous space is conjugate to the system. And in 2010, Tula proved that for finding a D-step nilsystem have a nilpotent enveloping semigroups. Moreover, in his paper, he gave an explicit description of those semigroups. Later, Donoso using the tool called cube space introduced by Hofstra and Mas generalized the Glassiner and Pigula's result to more general systems. Before introducing Donoso's result, we said something about the origin of the powerful tool cube space. A connection between a Gotier theory and the additive combinatorics was established by Fussenberg. He proved that actually the following multiple recurrence theorem can imply the similarity theorem. That given a measure preserving system for any positive integer D and a set with positive measure, the infimum of the average is positive. So in view of this theorem, it's natural to ask about the convergence of these averages, or more generally about the convergence of the so-called multiple Gotier averages, where the functions are bounded. In the study of multiple Gotier averages, the idea of characteristic factors play a very important role. The original idea was provided by Fussenberg. Usually finding a good characteristic factor for certain schemes of averages often use a reduction of the problem or of evaluating their limit behavior. For example, Footmerger showed that actually the measurable distal factor is a characteristic factor. And Hoskra and Ziegler independently prove that there exists a D-step characteristic factor, such that this factor is an inverse limit of D-1 step Nil system. Here we recall the definition of Nil systems. G is a D-step nilpotent group, and gamma is a discrete concavite subgroup of G. So the potent space is called a D-step nil manifold. Given an element tau in G and the letter T be the translation by tau, the pair XT is called a D-step nil system. So to get the corresponding factors in topological dynamics, in the pioneering work of Hoskra Mas in 2010, introduced the notion of the regional proximal relation of D. Given a system with a pair of points x, y, is a regional proximal over the D. If for any given distance, we can choose another pair which is close to xy, and times n1 to nd, such that the chosen pair is also close under the terms of the IP D set generated by n1 to nd. Okay, here we give a graph to show it. For the case D equals to 1, is nothing but the regional proximal relation defined before. And for the case D equals 2, just like that. And by the definition, there is a inclusion. So when and they also prove that for a minimal distal system, the regional proximal relation of any order is an equivalence relation. And also they prove that the minimal system is an inverse limit of D-step minimal Nil system if and only if the regional proximal relation over D is trivial. So we call it we call a minimal system a D-step pro-Nil system when the relation the regional proximal relation of D is trivial. Okay. Later, Shaw and Ye prove that for any minimal system, the regional proximal relation of D is also an equivalence relation. So the intersection of all such relation we can get a new equivalence relation, which is called the regional proximal relation of order infinity. And we call a minimal system infinity step pro-nilsystem if the equivalent relation is trivial. And it would prove that actually a minimal system is an infinity step pro-nilsystem if and only if it is an inverse limit of minimal nilsystems. Shaw and Ye also prove that for any minimal system, the projection of the regional proximal relation of the D on X through the factor pi equals to the one on the factor Y. This property is called the lifting property. And the second one is that the factor is a D-step pro-nilsystem if and only if the regional proximal relation of D on X is contained in the fiber. So in particular, the quotient is the maximal D-step pro-nil factor of X. The maximal means that the second property. It should be noticed that in their paper, they only prove this theorem for positive integer, but by similar argument, we can show that for the order infinity is also hold. So we may ask naturally that is there a nilpotent structure that is given a factor such that the factor is a system of the D if and only if the regional proximal relation of the D on X is contained in the fiber. We know that this holds for the case D equals to 1. Okay. Back to this question. Here we and the mean-modulity assumption, as we want to use the nilpotent structure. But this theorem only holds for minimal system. So in this table, the right hand is maybe pro-nilsystems. So what we need to do is to seek a good class of groups. Set A is said to be a red topological group if it satisfies other. The first one is E is a group, and the second one is E is a compact space, and also the it also satisfies that the red translation is continuous. And in this talk, a Hausdorff red topological group will be called Alice group for short. We know for distal system, it's an enveloping system, enveloping semi-system, semigroup is an Alice group. The following definition on Alice group was given by Donoso in 2014. Given Alice group E and the subset A and B, we can define this as the closed subgroup spanned by the commutator of A and B. And we can define the topological commutator subgroup inductively as follows. And we said that the E is a D-step topological nilpotent if E sub D D plus 1 is the trivial subgroup. Here I and a condition that the E sub D is non-trivial. This condition is necessary because the latter trivial groups bring nothing for us. So here is a question: why we use a top nilpotent instead of nilpotent? Because the example given by Gartner and Piccola both show that the nilpotent is enough, and I will explain this later. And also this is very important. So if it is a D-step top nilpotent Alice group, clearly it is a D-step nilpotent group. Also, the last non-trivial top commutator subgroup is a compact abelian group. And we prove that actually in his definition, what we should do is to first is the topological commutator subgroup is just the closure of the commutator subgroup of E sub J and E. With these notations, Donoso proved that for a minimal D-step pro-nilsystem, its enveloping semigroup is a D-step top nilpotent group, and thus a D-step nilpotent group. Conversely,
excuse me, can you show again the previous slide?
Yeah.
The one where you defined E top.
E1?
E top. The topological filtration of Donoso. It was 2 slides before. Before? One before, can you please? I'm asking about this one.
Yeah.
Ah, okay. The topology, the closed group spanned. So I don't understand this subtlety. Why this is not the same that was before? Why is this a theorem?
In his definition, he requires this is a closed subgroup, and I prove that for example, when j equals 1, in his definition, we need so in his definition, the group is larger than this. So it's just a closed set, but not might not be a group.
It's the closure of an algebraic group, right?
Yes.
Whereas there it's the smallest topological group which contains the algebraic group. That's the difference? Or the smallest closed subgroup which contains. That's the original definition, right?
Yes.
Okay. Okay, I see. Thank you.
And he proved that if a minimal system has a two-step top-nil enveloping system of same group, the system is a two-step pro-nil system. That is the original proximal relation of the two is trivial. Given a distal system with a d-step top-nilpotent enveloping semigroup, and we know that the last non-trivial subgroup is a compact group, but just in the point-wise topology. So if we want to define a group extension, we need the uniform topology, and the following theorem guarantees this. So we can define a equivalence relation as follows. And so we can build a cotton. And Donoso proved that actually x d-1 has a d-1 step top-nilpotent enveloping semigroup. Moreover, it is a maximal factor of x with this property. This means that if there is another factor y over x also has a d-1 step top-nilpotent enveloping semigroup, then y must be a factor of x d-1. If the system is minimal, then this factor is an extension of the maximal d-1 step pro-nil factor. So according to this method, we can get a sequence of factors such that xj is an extension of x j-1 by the compact abelian group. So when the system is minimal, we can have the following commutative theorem. So he conjectured that if a minimal system has a d-step top-nilpotent enveloping semigroup where d is not less than 3, then the system must be a d-step pro-nil system. And our work is to confirm his conjecture. so combining his result, we can get that a minimal system is a D-step pro-nilsystem if and only if the enveloping semigroup is a D-step top-nilpotent group. We next show how we prove it. Inspired by the nilpotent structure theorem, we want to reduce to a general case to a nil system case. This process is divided into two parts. The first part is that we assume that the system itself is a nil system. That is to prove that any minimal nil system with a D-step top-nilpotent enveloping semigroup is a D-step nil system, and this step is easy. And the second part is that reduced to the maximal nil factor, and this is to show that any minimal system with a top-nilpotent enveloping semigroup is an infinity step pro-nil system. That is the original proximal relation of infinity is trivial. Once we prove, and this can confirm Donoso conjecture. So for the first part, we study the Photonberg tower of a minimal nil system. We know in 1963, Photonberg gave the following theorem about the minimal distance system. He proved that any minimal distance system is a transfinite composition of isometric extension, and we call this sequence the Photonberg tower. Given a nil system, we can define the vector as this, and so we have this descending sequence of vector between nil systems is so is this sequence the Photonberg tower of the nil system, and we confirm this thing, confirm this, and show that actually the maximal isometric extension of ZR below X is the R+1. So using this, we can show they prove that actually this factor is also the maximal R-step pro-nil factor of a nil system. So we can and using this we can confirm the Donoso's conjecture for nil system. The proof is trivial. We let ZJ donate the J-step pro-nil factor of the system, and by induction we get xj equals to this year. And also, we also have the following commutative degree. What we need to do is to show that the factor pi is trivial. Otherwise, x2 ZD is also if pi is not trivial, the x2 Z D minus 1 is not isometric, so it is a contradiction. To finish the second part, we need a powerful tool called cube space. So the following are some notations. And in the discrete cubes, here is some examples. And in discrete cubes, we can define some different faces. That is fix some coordinate. We give an example. So in the first one, the face in red color is a codimension of codimension 1, and also have dimension 2. And the third example has a codimension 2 and all have dimension 1. A trivial factor is that a face can be divided into the united of the subfaces or over higher codimensions. So we can define the Haussler cube group. The Haussler cube group is defined as follows. Where the F ranks all over faces of codimension 1. Here are some examples. And here is for codimension 2. And for a abelian group, a cube group can have a good representation. The first is that in the definition, we need to consider all faces of codimension 1, and here we claim that we only consider the up face. We only need to consider up face and the diagonal element, and that's enough. So we can say that every element can be written as this. So for dynamical system, we can define the cube space as follows, and it was proved. Shao and Ye proved that actually, if the system is minimal, then the cube space is also minimal under the cube group. And the most important is the following, that we can use the cube space to characterize the regional proximal relation of a higher order. That is, if xy is regional proximal of order D, then if and only if xyy belongs to the cube space. So I can explain why we use top-nilpotent instead of nilpotent. Given this distal system, we know that the cube group of dimension 2 is generated by the following 3 generators, and we let this be the enveloping semigroup of the system. Why we use not the cube space? The reason is the following. That is, we can put the enveloping semigroup to a larger systems. So from this we can deduce that for any PQR belongs to the enveloping semigroup, we have this. So we make a commutator, and we get that Q, we get this. So for any, so we can get this for any it belongs to E2. We know that this set is closed, so we can get this. For any S belongs to E2 top. We all have this. So and also we have this. So for any X, XX belongs to the cube space. But we know only when the system is minimal, we can use it to we can deduce that the X and SX is regional proximal. Only when the system is minimal. So for higher dimension, the argument is similar. So given a minimal system with a step top-nilpotent enveloping semigroup, the system, the cube system, cube space is also minimal and distal. So so we want to compute its enveloping semigroup. In particular, is it a D-step top-nilpotent? But here are 2 difficulties. The first one is that, unlike a nilpotent group, the commutator of 2 elements we have only we have only this. But for nilpotent group, the commutator of x, y belongs to ei plus j. So here is a difficulty. The following is that given 2 nets P alpha, Q alpha, we let P alpha convert to P and Q alpha convert to Q. But we don't. But for topological group, we know P alpha, the product of P alpha, Q alpha converted to the product of P and Q. But for Alice group, we cannot compute this limit. For the first difficulty, here we I give a upper bound and of this form. As we see, the commutator of x and y belongs to Ej plus 1, and the intersection of f and s. Oh, sorry, the codimension of the intersection of f and s is not more than ai plus aj. So we can get this. So here is a condition that ai plus aj is not equal, not more than aj plus 1. So I choose this. And we prove that the set we defined satisfy the following properties. The first one is this can be obtained by the definition, but the oh, sorry. If this theorem is right, then we can get that we can give a upper bound of the Alice group of generated by the cube group, and also his topological commutator subgroup also have a bound. The first statement is trivial. Just follow the definition. So we just prove the second statement. We show it by the induction on the nilpotent class. So there is a question: can given a normal subgroup of E close the normal subgroup of E, and can the cotant group with the cotant topology be a Alice group? Here we provide a condition that if this group, if this subgroup is included in the center of the group E, then the cotant group with the cotant topology is an Alice group. And we know that ED top is satisfies this condition. So by induction, we can show that if this Alice group is a top-nilpotent, is a top-nilpotent, then we get the cotant group also top-nilpotent. Okay. Using Alice joint continuity theorem, we can get the joint continuous. As we said, for general nets, we can't control the limit, but if the Q alpha is good enough, for example, if Q alpha is included in the center of the group E, then we can compute this limit. We show that actually the product of P alpha and Q alpha converges to the product of P and Q. So with this result, we can show the following result. That is the so with this result, we can prove that this set C1 is closed. We give an example for the case D equals to 2 to show it to show how we prove it. The first is we can get a quotient group, and it's also a abelian compact group. So as the topology on G is a quotient topology, so the pi is continuous. And we know that C1J is closed in the product group. So as the pi is continuous, so the prime image of the set is also closed. So we can it's clear that this set is also a group, as E2 top is included in the center. So we get this set is a group and also a closed set. So it's an Alice group. So we can get a quotient group, and this group is also an Alice group. So given a net in C1, and let G alpha converges to G, and we know that the G belongs to this set. Also, consider the projection on W. We also get this convergence. So for every alpha, we can write alpha as this, or where Fi is a factor of codimension 1, and Fj is a codimension 2, and we can assume that every Gi alpha converts to Gi. So we put them in W. We get this. As W is a abelian group. So from this we can Also, the W is out of space, so we get this. And from this, we can show that G belongs to C1. This shows that C1 is a closed set. Okay. And we still need the following result. Here G is a abelian group. That is the maximal factor of all the infinity of the cube space is the cube space of the generated by the maximal factor of all the infinity. And I will explain later why we use this. So with this result, we can finish the second part. That is for any. Here we prove that for any abelian group. For any abelian group action, minimal system with a pro-nilpotent developing semigroup system of the infinity. That is the regional proximal relation of infinity is trivial. We show it by the induction on the nilpotency class. We know we can build a factor by this. So by induction, x d minus 1 is a system of the infinity. So we get the conclusion. We know that the factor also has a d minus 1 step top-nilpotent enveloping semigroup by the induction. So we get the following factors. As we have proved that this is the maximal factor of infinity of the cube space. So this factor is a factor of this. Okay. So we can find a Q in the last non-trivial subgroup or such that x equals qx. And for a larger system, there is also an element such that qy equals py. So we can get this. And we can deduce that p equals to this. Why we can get this? Because p is belongs to ED top, and this is the this is included in the automorphism of the system. So this so we can get this. But from this we can deduce that the P is identity. The reason is following. As the ED top is included in the CD, as we defined before. And here, CD is defined by this. And so as the ED top is a abelian group, so we can get the following equation. This shows that P is identity. This shows if P is identity, this shows that X equals to Y, and so the regional proximal relation of infinity is trivial. Okay. Here we give some open questions. The first one is the nilpotent structure. We have given before. That is given a factor that Y is a system of D if and only if the regional proximal relation of order D on X is contained in the fiber. The second one is related to this. That is, we conjecture that for any system, does this also hold? And the third question is for my personal interest. Now we can consider a general group action, and we sum this system is minimal, and also with a disturbed top-nilpotent developing semigroup. And we also can define the idea as this. And using the result before, we can show that every idea is an equivalence relation. So we can define the factor by this. So I want to know what is the property of XJ. For J equals 2, we know that this is X2 is just the maximal equal continuous factor. So why this is an equivalence relation? The proof is trivial. Gamma invariant is trivial, and as this is a group, so the transitive can be proven, and what we should prove is that this set is closed, and use use this result. We can deduce that this set is closed. So every idea is an equivalence relation, and XJ, the factor XJ has the J-step top-nilpotent enveloping semigroup. So okay, my talk is over. Thanks for listening.
Any questions?
Yes, I would like to make a remark. If I understood correctly, in the beginning, you said that the Lie semigroup is metrizable if and only if X is equicontinuous. And actually, there is a paper by Glasner, Megrelashvili, and Uspensky, which shows that the Ellis semigroup is metrizable if and only if X is something which is called heritedly almost equicontinuous. And in that paper, they also construct an example of a system which is not equicontinuous, but is usually you use the shortening H AE. It's not equicontinuous. It is HAE, and its Ellis semigroup is metrizable.
Any other questions, comments? So, no other questions or comments. Let us thank Jiahao again. Thank you for the nice talk.